Hello friends, we are seeing the curve settings in the unit 5. There are two methods available, linear method and angular method. In that we have started the linear method in the previous video. In this video we try to complete the linear methods available for setting out the curve. The second one is the by successive bisection of arcs or chords. See, when we need to set this is the tangent which is going to be produced and going to meet somewhere else at intersection point I or V, the tangent B, right? So this is the T1 point, this is the T2 point, this is the curve to be setted, and this is the exact midpoint C of the curve. If you join that C to the midpoint of the long chord, that is the mid-ordinate O0. From here, C, if you join T1 to C, you will get another chord, right? In that, this become another arc, right? So this arc, then again we can bisect into C1 D1, right? So similar pattern you can follow. Again this C1 T1 become another arc, we can bisect here, right, until we get the curve very smoother. This is the methodology, that is the successive bisection of arcs or chord. Here we are bisecting the chords also and we are bisecting the arc also, right? And the formula to determine the O0, the mid-ordinate for any, see, this is the mid-ordinate, this is another mid-ordinate, this is another mid-ordinate, this is mid-ordinate. It is depends upon what the radius of the curve and the L, that is the long chord length. So L minus root of R square minus L by 2 the whole square. That is the point here. You have to remember the O0 is the concept of this curve. Predominantly for very precise works only, this type of methodology they will adapt. So you try to remember the formula alone. So here C T1 T2 is again L, T1 C is also L. If you consider this is a L, for that this L distance has to be substituted, right? See here the R doesn't get changed. If you join here also, this for this arc also the R is same, but the length of the chord is get changing, right? T1 C, this is the L, T2 C again L, then C1, C1, this is the length, and C1 T1, this is the length. So by bisecting the chord and the arc, so if you change the value of the L, you will get the mid-ordinate value. Based on that mid-ordinate, you can mark the points, and if you join those points, you will get the smooth curve, right? Next method is offset from the tangent. For the curve, we know back tangent and the forward tangent. So from T1 to the V and from T2 to the V, there will be two tangent. Either one tangent we can consider. From that tangent at x distance from the T1 x distance, if you drop a offset to the curve radially, or if you drop the offset perpendicular to the tangent, here radial to the tangent, here perpendicular to the tangent, we will get this OX distance to be determined, this OX distance to be determined. So which is root of R square plus X square minus R. Here it is R minus root of R square minus X square. You don't get interchange these formula. These are the exact formula. How the derivation? Let's see. For the radial offset T1 to the intersection point, we are considering a x distance, say at a point P. and it is the origin of the arc, and it bisects the arc at P dash, and it produces up to P. So we need to determine the P dash distance, that is OX, radial offset from the tangent. We need to determine, right? How we can determine? You remember this diagram, you need to draw this. Radial offset from the tangent, OX is the radial offset P dash at any distance x along the tangent T1, we have shown in the figure, from the triangle OT1P, from the triangle OT1P, OT1P, this is the 90 degree, since it is a tangent point, so in a right angle triangle we need to determine the x, right? So this, what is the angle here, right? From that angle you need to determine the OX we required for the x distance, right? So cos, we can have R is known, and R plus OX, that is the thing, total distance. So R plus OX the whole square minus R square, which gives the x square. So from the triangle OP square is equal to OT1 square plus T1P square. So R plus OX the whole square is equal to R square plus x square, right? So same, the Pythagoras theorem only we have adapted. From here, see, if you take the square root, R plus OX equal to root of R square plus x square, and OX we required, so R square plus x square the root minus R, right? This is the exact expression we have shown here, right? R square plus x square minus R. For calculation and all the things in the setting out, we have to consider this formula only. For making approximation, say if you make R outside to the root, 1 plus x square by R square the whole power half minus R, right? And if you expand that expression, 1 plus x square by 2R the whole square plus x power 4 plus 8R power 4, it's keep on going minus R. See, R itself higher value, R square, x is very small, so this itself is small compared to this x power 4 by it is so we can negligible up to this. So R into 1 plus x square by 2R the whole square minus R. So if you expand it, R minus R get cancel, x square by 2 R square, 1 R will product will cancel, x square by 2R. So this is the approximate expression OX equal to. For radial offset also the same expression you will get for the perpendicular offset, but the difference here is the exact expression gives root of R square plus x square minus R, and for that it is a different, right? See, for the perpendicular offset, same diagram, instead of we are dropping the radial offset, we are dropping exactly 90 degree offset from the tangent, right? OX. Here also we need to determine the OX. So this OX is exactly parallel to ET1. So we mark a point ET1 and the same x distance P dash, and here it is P. The notations are same, but extra E is new one. Now this forms a right angle triangle, right? From that, if you are able to get this, and we can correlate this x, and from that you can determine the OX. See, in the triangle OEP dash, OET dash, this is P dash. P dash O square is equal to OE square plus P dash E square. That is again the Pythagoras theorem. So R square, is equal to OE square plus EP dash square. R square is equal to OE square plus P dash E square. P dash E is, again you know, it is x square. OE, see, O T1 is R. From that we have to subtract T1E, right? So O T1 minus E T1 the whole square. OT1 is R minus ET1 is OX the whole square plus x square. We need to determine the OX, so we are shifting the x square here. So R minus OX the whole square is equal to R square minus x square. Taking the square root, you will get R minus OX is equal to root of R square minus x square. So OX equal to R minus root of R square minus x square. There the expression is, for the radial offset, it is R root of R square plus x square minus R. Here the expression is R minus root of R square minus x square, right? So this is the difference. This has to be used for the calculation. For the approximation, again we make the same square root combination and we are expanding the expression. This will become the neglected one. So if you product the R inside, you will get R minus R get cancelled, minus into minus plus, this R will get product, so x square by 2 are the same expression which we get in the radial offset. So from that we can't conclude both the radial and the offset are same, since here the difference is, for approximation we can use this, right? So assigning different values to the x, the corresponding values of offset OX can be calculated. These calculated offset can be laid from the tangent at known distance x, and the points can be established in the field, which when joined produce the required curve, right? I hope we have completed the linear methods. I hope you understand, friends. Thank you.